Welcome back to this video. Now we are going to do the cascade method after the composite curves method. Here's the thing. I have already did this video. It's just that I had to restart it again due to glitches. So I was far with the video, but it's fine. I'll just explain what I have covered so far. So number two, we are using cascade method, of which we expect to get the same answers as the ones that we did for the graphical method. So now here's the thing. For cascade method, this is a table that we're going to make use of, okay? So we have our streams H1. We have our streams H1, H2, C1, and C2. Let me do this. Check something if this is visible. Okay, it's visible. We have C1, we have H1, H2, C1, and C2, right? So remember, this is the given information as well as this side. The one in the middle, it is the one that we had to do it by ourselves. So for hot streams, remember, we're given delta T minimum to be 10 degrees Celsius. So what we're going to do is we're going to take half of that temperature, and for the hot streams, we minus that half of 10 degrees Celsius. For the cold streams, we add that half of 10 degrees Celsius. So that's how we manage to change these temperatures for the supply and the target. And the ones that we have added and subtracted half of T minimum, we indicate them by the asterisk at the top. So meaning for H1, our supply will now be 245 to 35, H2 195 to 75, C1 25 to 185, C2 145 to 235. And then now we jump to table number two. Table number two, this is where we're gonna take all of these temperatures, but we're gonna write them in descending order, meaning we're gonna start with the largest and then we're gonna end with the smallest. So we're gonna start with 245 at the top. There is 245 followed by 235. There is 235 followed by 195. There is 195, 185, 185, 145, 145, 75, 75, 35, 35. At the end, we have 25. And then after doing that table, after doing this, we do our streams, right? We have two hot streams, we have two cold streams, and then we have delta H, E, sum of CP cold minus sum of CP hot. And what I've realized is that some other people, how they write this, they write it in the form of sum of CP hot subtract the sum of CP cold. Some textbooks, they write it like this. Some people, they solve it like this, which is not wrong. The reason is why we are doing this is because we're going to compensate for that during our calculations. Do you understand? You can do it like this. It is just that when we get to the cascade, we will be subtracting. But if you do your CP like this, when you get to cascade, you have to add. But if you do it like how I did it, CP cold minus CP hot, then you have to subtract on your cascade. Ne? Right. So this will be compensated. And then our delta H, what we do is, again, the thermodynamics equation, delta H, it is given by Cp multiplied by change in temperature. So in this case, we're going to have to multiply these of Cp's and the change in temperature, and then we get all of these numerical values over here of our delta H in kW. By the way, the units here will be kilowatts. And then after that, okay, maybe you want to understand how did I get these temperature differences? So within this interval between 245 and 234, I subtracted and then I got 10. Between 234 and 195, I subtracted and then I got 40. Between 195 and 185, I subtracted and then I got 10. So you can make mistakes. So not that you do not know what you are doing, but you can make mistakes. So try to be careful a little bit about that, okay? When you perform your calculations. Because sometimes, like I normally do mistakes. Instead of B195, I would say 195 subtract 184 instead of 185, and that will automatically affect my whole calculation. Okay, so mistakes can happen. Also confirm the delta t's are correct. And then sum of CP cold minus sum of CP hot. What did I do here? Sum of CP cold. I go in this interval. Do I have a cold stream? I do not have a cold stream. I only have a hot stream. So, and it's only one of it. So cold is going to be 0, but the hot is going to be 0.15. So I'm going to say 0 minus 0.15, and then I'm going to get 0.15. It's too noisy here. Yeah, no, let's continue. And then within this interval, how did I get 0.15? It's within this interval. Sum of cold, we have only one cold stream, which is 0.3, minus sum of hot, we have only one hot stream, which is 0.15. So I'm going to say 0.3 minus 0.15. Definitely, we will get 0.15. And then within this interval, I'm going to say sum of cold. I have 0.3, right? It's only one that is cold. And then subtract the sum of CP for hot. For hot, I have two of them, which is 0.25 and 0.15 within 195 and 185. So these two guys, I'm going to have to add them. And I'm going to say 0.3 minus the sum of these two guys. And then I'm going to get negative 0.1. And then within this interval, I have cold, cold, hot, hot. Within this interval between 185 and 143, I have these lines and this line and this line and this line. So I'm going to say this plus this, subtract this minus this plus this, right? And then I'm going to get 0.1 and so forth. And then to get this, like I told you, I'm going to make use of this equation. I'm going to multiply this, guys. This multiply by this will give me that. This multiply by this will give me that. This multiply by this will, and so forth. And then from there, what we're going to do is we quickly get to our cascade. Now, this is where I kind of made a mistake. So that's why I had to restart this video again, okay? Like I said, mistakes bound to happen. So what I'm going to do is now I'm jumping here, which is this is step 1, step 2. Now this is step 3. Now step 3, over here, what you have to know is on the cascade, we have the cold utility at the top. We have the hot utility at the top. Hot utility. And then at the bottom, we have the cold utility. Right? So now, in this cascade, how did I design this cascade? It's simple. All of these temperatures that you see on this side, I literally took them from here. I took them from this side. Okay? And then I'm going to take all of these delta H values and then I'm going to put them inside of these rectangular shapes. Right? Right. So now, how are we going to perform a calculation over here? Like I said, I am going, firstly, we start with 0 kilowatt, which is our energy. I'm going to say this guy subtract this guy. We are minusing. I'm not adding. That's what I'm saying to you. This is where I am compensating for this difference that I got over here. But if I did it like this, I was gonna add moving downwards. You get my point? So here I will be minusing. So I'm gonna say 0 minus 1,5. That will give me positive 1,5 kilowatts. And then I'm going to say 1,5 minus 6. That will give me negative 4,5. And then I'm going to say negative 4,5 minus 1. That will give me negative 3,5. And then I'm going to say negative 3,5 minus 4. That will give me negative 7,5. And then I'm going to say negative 7,5 minus 2. Negative 7,5 minus 2. And then that will give me negative 7,5. You see, this is how I made a mistake. So negative 7,5 minus 14. That will give me 6.5. Like I said, mistakes are bound to happen. So be careful when you do these things. and then 6,5 minus 2. I always make mistakes. I don't know why. Maybe my brain is tired. And then we get 4,5. And then 4,5 minus 2. And then that will give us 2. That will give us 2.5. Awesome. Now what we're going to do is from this cascade to the, now we say this cascade, it is infeasible. Okay, it is infeasible because we cannot locate for our pinch temperature. Why? How do we see that we cannot locate our pinch temperature? It's because there is nowhere where we have 0 kilowatt. So where you have your 0 kilowatt, because we assign the 0 kilowatt for ourselves, we want these calculations automatically to give us 0 kilowatt, so that we can take the corresponding temperature to that 0 kilowatt. And that temperature will be our pinch temperature. We're going to make use of that temperature to determine the pinch for hot and the pinch for cold. So that means this cascade, we will consider it as infeasible. So let's see if this cascade will be feasible by helping us to determine the pinch temperature. So how are we going to make use of this cascade jumping from here to here? We cannot just jump because we want to. We jump because we make use of this cascade to get here. So what we're going to do here is jumping from here to here, we're going to take the most negative value, the most negative delta H. The most negative delta H, it is the one that's going to open up here at the top. So when you have a look at your delta H values, we have negative 7,5 to be the one that is the most negative. So since, well, this is a negative one, the most negative one, it's going to open up our second cascade, which we assume we would want this to be feasible. So meaning we're going to take that 7,5, but don't take it as negative, rather take it as positive kilowatt. Don't forget that this then will serve as a hot utility. So this is what our heater requires to warm up the remaining cold water. Okay, and therefore now what we're going to do is we're going to perform the same thing, the same calculations. So we're going to say 7,5 minus 1,5, that will give us 9. 9 minus 6, that will give us 3. 3 minus 1, that's like 3 plus 1, that will give us 4. And then 4 minus 4, then that will give us 0. And then 0 minus 14, that will give us positive 14. 14 minus 2, that will give us 12. 12 minus 2, that will give us 10 kilowatt. And therefore this will be cold utility. So we need a temperature of what? What's this value? 20. Yeah, this will be the cold utility. So now, here's the thing. Where we got 0, it's here, right? What's the corresponding temperature? It's 45 degrees. So that means the pinch temperature, it will be 145 degrees Celsius. But now here's the thing. It is the pinch temperature. We can make use of this to determine the pinch for hot as well as the pinch for cold, of which the delta T minimum between is supposed to be 10. So by doing so, for hot, we are most definitely for hot, we are doing what? We're going to take this numerical value, which is 145 degrees Celsius, and we are going to add 5 degrees Celsius, right? This will give us 150 degrees Celsius. And then for cold, this is what we are going to do. The very same numerical value. We subtract 5 degrees Celsius, and this will give us 140 degrees Celsius. Recall that delta T minimum, which is 150 minus 140, supposed to give us 10 degrees Celsius, which is delta T minimum. So if you still do remember, we did the graphical method, right? And then we got that our temperature here, it was 150 for hot. Our temperature for cold, it was 140, of which now it is corresponding exactly with what we get now when we use the cascade diagram, right? And then the other thing is the cold utility and the hot utility. So here we got a little bit different values. Here it's 15 kilowatts for our QC minimum, which is cold utility. And then here our cold utility it's 10. Okay, it's far, but yeah, it's far by 5. And then this side we got our hot utility to be 12.5. And then us over there we got 7.5, which is again from 12.5 to 7.5. That's the difference of 5, just like here and there. So in this case, for accuracy, we add 5. And even there, we also add 5 for accuracy purposes. Or we subtract 5 on the graphical method for accuracy purposes to get this exact same values that we see over here. So yeah, obvious, this won't be 1000% correct because it's a graphical and we use the freehand drawing. And yeah, so this is how we do it. So this is a pitch point for hot, pitch point for cold. And then we have our utilities for cold and hot. And this is the end of the session.